Log on, tune in, find out. Another good idea from Cambridge.
Well, I spoke once before in the seminar at the department, and this talk in some way is a sequel to that talk, although it's completely self-contained. You don't need to know anything that I said, but sort of the motivation comes from there. What I'm going to speak about today might seem a little bit frivolous as a topic in its own right. So it's a little bit funny that this one is going out on streaming video all over the world, and the other one did not. But that's the way it is. What I'm going to talk about today, well, everyone knows Grothendieck's theorem that says that if G is a reductive group, that principal G bundles on the projective line all reduce to a maximal torus. And you might think that P1 is the only base space where that could possibly happen. It's certainly false for curves of higher genus. It's certainly false for varieties of higher dimension. But what I'll try to convince you is that, in fact, if you dig a little bit, there are lots of other base spaces where this kind of statement could be true. And there's some value to knowing this. So the reason why we would want to know these things, the applications, were what I talked about last time. So I won't talk about that. Instead, this is just going to be sort of a series of examples, counterexamples, and results, none of which is extremely deep. There are some subtleties. But it's more just to point out that, Grothendieck's theorem does have some extensions. There are some broader situations where this kind of statement is true. So the paper, maybe I should say before I forget, that as with the last talk, this all represents joint work with my former student, Johan Martens, who will be here next week. Unlike the last one, the paper about this is not finished, but it will be called something like Variations on a Theme by Grothendieck, because that really is what it's about. So, the setting is that I want G to be a split reductive group. That is a reductive group whose maximal torus is a product of multiplicative groups. So let that maximal torus be T. And these could be defined over any field K whatsoever. As I like to say, there's a very small part of algebraic geometry that's valid over an completely arbitrary field, but this is part of it. And the objects that we're going to study are principal G bundles over, well, first over P1, so locally trivial principal bundles. You could assume that they're locally trivial in the Zariski topology, or, all right, with some mild assumptions on the field, you could even study bundles that are locally trivial in the Untitled topology. Okay, so I forgot to look up exactly what the correct hypothesis on the field is that the field of rational functions, kt, have cohomological dimension 1. So that's true when k equals, when k is algebraically closed, when the characteristic is 0. Yeah, in a wide range of cases. And then, so Grothendieck's theorem, right, says that every such bundle reduces to a maximal torus. But I actually want to spell out, so I should hide these four things where I can get them out later. At some point I may have to give up and erase them. There are really four results that are, some due to Grothendieck, some to Harder, Narasimhan, which are interlocked and interrelated. So the first is that such a bundle does reduce to T, reduce to a maximal torus. So what does that mean? I mean, people like to say, in gauge theory, that the structure group of a bundle reduces to a subgroup if there exists a principal T bundle so that the original bundle is obtained by extension of structure group. But I want to be a little bit more precise and say, well, consider the associated bundle, just the quotient of E by the action of T. The associated bundle, homogeneous bundle, a reduction consists of a section of this homogeneous bundle. And then if one looks at the inverse image of this section in in E, and one calls this ET, then this is a principal T bundle. Oh, by the way, I'm using, as you see, this notation where this angled arrows, right, always refer to a locally trivial fiber bundle of some kind, as in gauge theory. So I'll try to explain whether I mean a principal bundle or some other kind of bundle, depending on the context. But here, what I mean is that then, if I have a section of the associated G mod T bundle, then I get a principal T bundle, and and then E is the associated G bundle. Yeah. So that's the first statement is that such a section always exists. But the reason I specify this so pedantically is because the next thing I want to say is, what does it mean to say that such a section is unique? That it's not completely unique. Such sections do to form. I mean, right? The example to keep in mind is where G is GLN, and then this says that every vector bundle splits as a sum of line bundles. But the splitting is not completely unique. I can certainly just deform with an automorphism of the bundle. Or, of course, I could permute the bundles. I mean, O plus O1 is isomorphic to O1 plus O, right? So, so the point is that there's a group which acts, namely the group of global automorphisms of the bundle, which acts on the left, and the Weil group, which acts on the right, right? The Weil group acts on the right on G mod T, and it therefore acts on this bundle. So this group acts on the sections, and the correct statement is that this section is unique modulo the action of these two groups. So you know, every vector bundle splits on P1 splits as a sum of line bundles. Those line bundles are unique modulo automorphisms of the bundle and permutations of the line bundles. So that's the correct statement. And hence the isomorphism class, of course, of ET is unique mod W. The Weil group W acts on T by outer automorphisms, and so if I extend by the structure group of one of those automorphisms, it takes ET to a different T bundle, but not very different. It's just a difference, again, between O plus O1 and O1 plus O. So then the third statement, oh no, well, I may not have room for all of them on this board, but the third statement is the version of the Hardo-Narasimhan reduction that is valid in this situation, which is that if one chooses a Borel and makes a choice of the simple roots or of the Borel containing the torus, then for any principal bundle, as up there exists a unique parabolic subgroup P containing the Borel and a reduction, so let's call it SP, a section of the associated G mod P bundle, satisfying three properties. First of all, that this reduction reduces further down to the torus. So one could say that the projection of SP is ST. Secondly, this reduction is rigid. It has no infinitesimal deformations. And thirdly, it's minimal. Among all reductions satisfying the first two properties, I can't reduce to a smaller parabolic subgroup and retain the properties 1 and 2. So, of course, again, the example is suppose I took a bundle whose splitting type, a vector bundle whose splitting type had some repeated factor like O2 plus O2 plus O3. Well, O2 plus O2 plus O1. The parabolic in question would be here the point is that the destabilizing subbundle that I could single out that is rigid is the sum of these two. If I tried to reduce all the way down to a Borel, then I could deform the line bundle O2 inside the sum of these two. So that's when I speak of the Harder-Narasimhan reduction, I mean this. And then, then fourthly, the automorphism group of every principal bundle on P1 is actually connected. And the proof of this uses C because, well, to prove that this automorphism group is connected, the first thing you show is that it's the same as the automorphism group of the bundle with parabolic structure group, EP. Okay, so these are this suite of results. And what I'm going to talk about is how each of these can be generalized to other base spaces. So let me sketch briefly how these things are proved. And this is not new material, but it's probably just as interesting or more interesting than the new material. And since, well, I should say the history is that A and B are attributed to Grothendieck, but they were proved by Grothendieck actually only over the complex numbers and using a mixture of algebraic and analytic methods. At the time when he was just making the transition from functional analysis to algebraic geometry, he spent a year in Kansas for some reason, and he wrote this paper in Kansas. It's a beautiful paper, but totally unlike his mature style. And then Harder, perhaps 10 years later, wrote a paper where he used algebraic methods, worked over an arbitrary field, and so on. Harder's paper is in German, and therefore I was able to learn about this much more effectively by reading a later paper by Ramanathan. So to prove part A, well, the first thing you do is that for GL2, or indeed for GLN, for vector bundles, this statement is really quite easy. One does it using Riemann-Roch. One finds the maximal destabilizing line bundle. One looks at extensions of that line bundle by a complement and so on. So for vector bundles, it's easy using Riemann-Roch. Now I want to reduce down to T, but let's first try to reduce down to a Borel. So look at the associated G mod B bundle, and then I can certainly find a generic section because I assume that this bundle is Zariski locally trivial. Or in these cases where I said it was okay to assume it was trivial in the Étale topology, that's precisely because this hypothesis on the field, which I didn't precisely state, there's that Steinberg theorem that says that if a field has cohomological dimension 1, then every homogeneous space over it has a point. So, so even in the Étale topology, one can find a generic section, a point of this homogeneous space But then, you know, G mod B is proper, so this generic extension, this just generic section, could be extended to a global section just by the valuative criterion. And so the reduction of structure group to B is not difficult. One wants to go further now and find, now one has a principal B bundle, one wants to find a section of the associated B mod T bundle to go all the way down to T. Now, if you chose the wrong reduction here, that might not be possible. You might get stuck. So the next step is to replace this reduction with another reduction that does go all the way down to T. So such a reduction is what Harder calls reduziert. But the word reduced means something else in English, so we call this an adapted section. As I say, it's somewhat easy to find any old section, but any old section might not be the right one. So what it means to be adapted is that for any positive root, alpha, on the Borel, I could take the associated line bundle to this. I now have a principal B bundle, EB, and I can take the associated line bundle, L alpha, so L alpha is the principal B bundle, EB, with structure group extended to GM. So it's just a line bundle on P1, and I want it always to have non-negative degree. So how do I know I can do this? Well, first, of course, it suffices to do it for the simple roots, because any positive root is a combination of simple roots. And then observe that G mod B is ruled by lines. For each simple root, there's a ruling of G mod B by lines, because there's a projection onto a G mod P for a next to minimal parabolic. You know, again, in the case of GLN, these are the lines that you get by just wiggling one subspace in the flag. Right, so for each simple root, G mod B is ruled by lines. And so inside this, inside this bundle here, if one looks at these lines, these give me PGL2 bundles, PGL2 bundles over P1, and we already did the case of GL2, right, with Riemann-Roch. Right, and on P1, every projective bundle lifts to a vector bundle. So the point is that inside that PGL2 bundle that contains the section I started with, I can find another section which is the the maximal destabilizing bundle for that rank 2 vector bundle. And that one, with respect to that root, the root that determined that ruling by lines, the associated line bundle is going to have non-negative degree. But none of the other ones are going to change, because I'm only moving around in that ruling. It's fairly clear that if I exchange the given section for a new section in that fashion, the other alphas remain exactly the same. So I just knock them off one at a time. If I have this, I can somehow get down to T, because, well, so the Borel subgroup acts on the homogeneous space B mod T. This is the non-normal subgroup of B, right? On the other hand, it's a semi-direct product. B also acts on the normal subgroup U by conjugation. And so even though, as varieties, of course, because it's a semi-direct product, B mod T is isomorphic to U, the actions do not correspond under this isomorphism. However, there's some relationship between the actions, and that means that the bundle EB mod T, of which I'm trying to find a section, this is a torsor for a bundle of groups. and not a principal bundle, right, but a bundle whose fibers have a group structure, the bundle associated to EB via the conjugation action on U. So this is a U bundle over P1, but not a principal U bundle. So it's a torsor for this, and then the point is that the sorry, what did I call this thing? I guess I didn't call it anything, but this is a bundle of groups, and since the unipotent is filtered by additive groups, by one-dimensional groups, this bundle is filtered by these L alphas. So by using long exact sequences, and since these all have positive degree or non-negative degree, they have no H1. It means that the classification of torsors over this thing is completely trivial. And so there is a so therefore this is isomorphic to that. It has a section, namely the identity section. So that's A. For B, well, I think the argument given by Grothendieck, in fact, is completely algebraic. So here it is. Again, the case of vector bundles is really quite easy. We're trying to show the splitting type is unique. Well, just again use Riemann-Roch to find a subbundle of maximal degree, and then split it off and go down by induction. So now, if you know the vector bundle case, you want to deduce the general case by looking at associated vector bundles to representations. So if I let lambda be the co-character lattice, homomorphisms from the multiplicative group to T, I mean, what we've shown is that every in part A we've shown that every principal G bundle is induced by extension of structure group from one of these. So so then I go on to GLN. For every representation rho, from G to GLN, I have isomorphic vector bundles. What that means is that if I consider my two co-characters going to T and then going into G, well, now I have isomorphic GLN bundles, and so I can it means if I take the trace of this representation, that gives me functions on the on GM. So the traces of these representations, of course, generate the coordinate ring of the space of conjugacy classes on G, which is the same as T mod W. This is an affine space. And so now I have two co-characters going into T. I know that their images in T mod W are equal. And so look at the image of the generic point in here, choose some element of W that takes the image of the generic point under lambda to its image under lambda prime. And that element of W then must interchange lambda and lambda prime. So that's how B goes. All right, so I'll skip C and D. and move on to telling you what are these other spaces besides P1 for which at least some of these results might be true. Well, for the most part, they're not schemes. One has to go to the world of stacks, but they're extremely simple stacks. They're one-dimensional stacks. The simplest of all are what we like to call footballs. These are not soccer balls. These are American footballs. It means a P1 with two stacky points. Well, let me draw something that actually does look like a football. Okay. All it means is a Lee-Mumford stack with 2 points with non-trivial stabilizer whose coarse moduli space is P1. Okay, something like that. So
the same stabilizer?
no, it doesn't have to. No, certainly not. That would not be so interesting. No, so let me define it this way. Okay, I take the stack A1 mod mu m, mod the cyclic group of order m. This has an open set isomorphic to A1 minus 0, and I glue it along that open set to A1 mod mu n. But since I'm working over any field whatsoever, I should specify that a football is said to be tame if both of these stabilizers are prime to the characteristic. And then theorem 1 says that A and B hold for tame footballs, but not wild ones. So the proof of A is really not so hard. And proof of A really just goes through exactly as it did before. Once you observe that there is a surjective morphism onto these footballs from a global quotient stack, I can take just m times n, or indeed the least common multiple of m and n, and I can look at this global quotient. And then this is what we were calling the other day an anti-representable morphism. It's a morphism which is everywhere surjective on stabilizer groups. But anyway, the point is that this sets up an equivalence between the category of bundles on the football and bundles on this bigger football. Well, or I guess the point is G bundles on P1 which are equivariant for the action of this group, and such that certain subgroups of the stabilizers act trivially at the two endpoints. And so one really just has to prove the statement for that. And there, well, because of the tameness hypothesis, I can sort of average. I find to do a part 1, for example, I find a subbundle of maximal degree. I look at its inclusion. I average that inclusion under all the elements of the group. And because the order of this group is prime to the characteristic, everything will work. So, so that part is pretty easy. Already with B, just to show that it's unique, the splitting type is unique, when there's a little subtlety. Which is that, well, we've shown that it reduces to a maximal torus. A maximal torus is just the group is split, so a maximal torus is a product of GMs. This is basically saying that that G bundles come from line bundles. But what are the line bundles on a football? With the isomorphism classes of line bundles, well, you can have sort of fractional line bundles that are coming from fractional divisors at the North Pole and the South Pole. So, so if you work it out, it's in fact z plus z modulo this lattice element, which may or may not be primitive. So let's call this P, this Picard group. If you think about the argument that I gave before here, the role of GM for a more general base space is going to be played by the Cartier dual of the Picard group. So, so the point is right. This group is isomorphic to of course, a product of a free abelian group and a cyclic group. So Q is the greatest common divisor of M and N. So this is still prime to the characteristic. And then, as I said, the Cartier dual, Hom from P to GM, is again a product of a multiplicative group and a cyclic group. And then, well, yes, it's still on the board here. So if you think about what happens, I just have to make this change. And it somehow turns out to be very important here, you see, that the group of components of this thing is cyclic. Because then I want to argue as before. I want to say, well, if I have two maps to here whose image and T mod W are equal, then they're actually equal modulo a global element of W. So how do I find that element of W? I choose the generator for this thing. I look at the generic point of that component. I look and see where it goes. You know, it goes to two elements of T that are interchanged by some element of W, and that element of W will take all of lambda to all of lambda prime. That's how it works. Yeah, so these are true. A and B are true for footballs. C and D, I'll expose them again down here. C and D are false. And when there are counterexamples, there always seem to be, in this game, there always seem to be elementary counterexamples. So that, well, ultimately that's just because the whole topic is sort of elementary. Already, if I just take, P1, 2, 2, which is just a global quotient of P1 by the action of a cyclic group of order 2. Sorry, I can't ever decide whether to write the cyclic group like this or like this, and I'm always going to choose it to be prime to the characteristic, so it's not going to matter. Anyway. Yeah, I mean, there's nothing quite like a Harder-Narasimhan stratification. There's no canonical choice of a parabolic because, well, for C, what if I just take the trivial bundle O plus O over P1? Now I just want to find an equivariant structure for this where there is no, canonical choice of a destabilizing subbundle, so to speak. Well, I'll just put weight +1 on this factor and weight -1 on that factor. So this now becomes a mu2 equivariant vector bundle over P1. And I could choose the parabolic that preserves this subbundle, or I could choose the one that preserves that one. And also the automorphism group of bundles over this thing do not have to be connected. And this has to do with the existence of disconnected centralizer groups in reductive groups. So as soon as I take a reductive group which is not simply connected, such as PGL2, then there could be elements with disconnected centralizers. So if I just take the trivial bundle on P1, and once again I want to make this into a mu2 equivariant principal bundle, so just let it act by, your favorite element whose, if this is regarded as an element in PGL2, then its centralizer is not connected, and that will immediately tell you that the automorphism group of E will essentially be that centralizer. Okay, maybe I should also say, of course, we like to put 2 orbifold points on P1, but even more we like to put 3 orbifold points on P1. And then somehow the game is over. Everything is false. Again, basically for elementary reasons, after all, what are bundles over these footballs or orbifolds? There's an equivalence between those and parabolic bundles. So there's an equivalence between bundles on this and vector or principal bundles on P1 with some parabolic structure. And again, if I just take the trivial bundle on P1 with 3 flags at 3 mark points, and those flags, do not split, I could take E1, E2, and then something that, anything that does not agree with the other two at these 3 mark points. This is an example of this provides an example of a GL2 bundle over this orbifold, which does not reduce to a maximal torus. Also, tameness is certainly necessary. Wow, that's just because if you choose any any representation of a finite group which is not completely reducible, then should I even write that? That leads to trouble, right? So if I take, say, P1 PP, which is P1 mod, all right, so now I do need to write Z mod PZ in characteristic P. Well, if I just take the 2-dimensional representation, which is not completely reducible, of this group in characteristic P, so I let that be V, and then this quotient becomes a rank 2 vector bundle over P1 and PP. This wild football, which again is just not, does not split as a sum of line bundles because the representation is not completely reducible. So a lot of this just has to do with sort of half-baking elementary facts and representation theory. So that's footballs. And then when I mentioned this to Jim Bryan a couple years ago, he said, well, of course you should also do it for finite abelian gerbs, which I did and which ended up wasting a lot of my time. But he's absolutely right that there's some slightly larger class than the class of footballs where the statement is still true. What do I mean by a finite gerb? Roughly speaking, I mean a bundle over a stack whose fiber is the classifying stack of a finite group. One might again fancifully say that these are like orbifolds, but they have orbifold structure at the generic point as well as at other points. So rather than try to give precise definitions of any of these things, I'll just tell you what are the stacks that I'm talking about. Again, I'll tell you just as I constructed a football by gluing together 2 quotient stacks. You should take the affine line, divide out by a finite group which does not act effectively, where there is a stabilizer at every point, and that stabilizer will be some group G. So that will then be an open set that is isomorphic to this, and I glue it to another thing, A1 mod delta.
I'm just a teeny bit confused over terminology. These are BG bundles over orbifolds, but they are still stable.
Yeah, that's right. Yeah, that's right. That's right. They're not orbifolds, but they're, well, but they're still Deligne-Mumford stacks, in fact, for the time being, yeah. Well, or at least tame stacks. So again, what's, nothing is deep, and yet one has to tread carefully. There's some statements are true, some statements are not true, and there's some fine line. So right here, gamma and delta are finite groups acting linearly on A1. One thing that's robust, by the way, maybe I shouldn't even mention this. It doesn't really matter if you glue using Z maps to Z inverse or Z maps to Z. You can glue, so P1, right? I glue together two charts like that, I get P1. But if I glue together like this, I get some non-Hausdorff space. And that actually would be perfectly okay. For those things, I also have, principal bundle should reduce to a maximal torus. Anyway, yeah. So the point is, the part that acts effectively, of course, is just a cyclic group. And the part that acts trivially is this normal subgroup G. Morally speaking, so I don't want to try and specify in what sense this is true. This is a BG bundle over the football, where G is this stabilizer group that acts trivially everywhere. So one could check that in this, you might ask, well, what about the band? It turns out in this setting, the band is always trivial. Wow, actually, no, not in this. Oh, sorry. I'll say that again later when it becomes true. Anyway, again, this is, we'll say that this is tame if the orders of these groups are both prime to the characteristic. And theorem 2 says that the Grothendieck results, AB, still hold for tame abelian gerbs, provided, and this turns out really to be necessary, that gamma and delta are themselves cyclic groups. So these extensions are just the most obvious extensions of cyclic groups by other cyclic groups. Otherwise, it's just false. Maybe we all know what A, B, C, and D are now, so maybe I'll finally erase them, right? A says is the existence of a reduction to T, B is the uniqueness of a reduction to T, C is the Harder-Nauer-Simon reduction, and D is the connectedness of the automorphism group. Maybe I could just summarize that somewhere. So C is Harder-Nauer-Simon, and D is yeah. Okay. So, in the setting of theorem 2, if you think about how do you prove A, there is another technicality, which is that, in the past, every projective bundle always lifts to a vector bundle. The Brouwer group would always vanish. And for these gerbs, of course, this is false. There are projective bundles that simply do not come from vector bundles. So there's some little tricky issue that one has to address there. We prove it for GL2 using some Riemann-Roch type approach. We want to use it for PGL2 because we have these P1 bundles in, what was it, step A3. Now, of course, there's always some tautological Z2 gerb over your space that you can construct where tautologically the projective bundle lifts to a to a vector bundle on that gerb. But that gerb would not in general be a cyclic gerb. So one needs to be careful. I mean, somehow, even though the structure group of that gerb is not cyclic, somehow one can make this work. Then in part B, the uniqueness, once again, what turns out to be relevant is this Cartier dual of the Picard group of this gerb. And so one again has to check that precisely in these hypotheses that I've given you, that the Cartier dual has a cyclic group of components. And therefore B works. Yeah, but so there must be counterexamples where B fails, but because this fails. Sorry, but I didn't prepare one for you today. Anyway, the point is that these hypotheses really are necessary. If you ever have stabilizers at the North Pole or the South Pole which are not cyclic, then again the game is really over. And again, it's simply because non-cyclic groups have irreducible representations of dimension greater than 1, and you can basically put those representations at the bad points. Sorry. Well, that's right. Yes, that's perfectly true. Right. So what's I do have counterexamples even for abelian. Right. All right. Let me continue. Maybe I'll come to yeah, of course, you're absolutely right. Maybe I'll come to a case where these are abelian, but this is still false. Sorry. Anyway. Yeah. Well. The example I was going to give was if I just take something like this, a quotient of P1 by a non-abelian group where the action factors through an abelian quotient. Well, then, so then I think you would agree, right, that if I simply choose an irreducible two-dimensional representation of this thing, that gives me a vector bundle on this quotient that does not split as a sum of line bundles. But what is an example where these stabilizer groups are abelian but not cyclic? Offhand, I don't know. And in fact, right, I mean, the real problem there might really, right, that's certainly going to cause problems with B. Right, that's certainly going to cause problems with B because then the whole point is that the Cartier dual of this, the Picard group is going to contain characters of the stabilizer group. Yeah, so right. What if I took just sort of P1 modulo some finite abelian group G that was not cyclic, and or even just P1 times PG, right? Yeah, exactly. The point is that the Picard group of this is isomorphic to that, right? And so if G is bigger than cyclic, then the Cartier dual is going to involve a copy of G, and then my argument for B is going to break down. So B would certainly be false in that case. And I mean, the uniqueness of a reduction. And then,
You might just have to expand. You might have to take into account. But I can't.
okay, yeah, well.
You might have to fix it by understandable amount. I only expect in the abelian case to sort of do splitting into line bundles.
Yeah.
You might still expect A to be true.
Yeah. Okay, well, I should have a look. I mean, I'm pretty sure that there are counterexamples, but I don't have them written down. I don't remember what they are. All right, but let me get on to the thing that really interests me. In the last 10 minutes, I mean, I spent a lot of time talking about footballs and gerbs. What really interests me are these chains that came up in my previous talk. And there somehow the situation is, type of argument one has to use, the situation is slightly different. So by a chain of lines, I simply mean a curve consisting of lines meeting along nodes. They have to be nodes because I definitely don't want the arithmetic genus to increase. And this is a scheme, by the way. I will point out this is the one other example that is a scheme. So theorem 3 says that A, B, and D, the connectedness of the automorphism group, all hold for chains of lines. But again, there's no sort of reasonable choice of a Harder-Narasimhan reduction. There's no kind of canonical choice of a destabilizing bundle or anything like that, because I can take O plus O1 on this component and glue it to O1 plus O on that component, and then, well, and there's clearly a problem, right? I have the reduction to the parabolic preserving this one or the one preserving that one, and those are both going to be minimal.
Again, this is, sorry, keep being grumpy, but this is because somehow there's no canonical choice of stability condition.
Yeah, that's right. Well, at least that's right. That's clearly related, yeah. Is that...
I mean, the K-theory is higher rank, so somehow it's going to be more choices.
Right, so I agree with that. So is that related to your previous remark? Okay, but now, I mean, now we're talking about chains, and before we were talking about gerbs, so...
So K-theory is also bigger than the stacking case. So it's only for P1 where the K-theory is only rank 2, but somehow more or less you've only got the rank and the degree and only one sort of stability.
I see.
I mean, this shouldn't be, I'm just saying this shouldn't be surprising.
Right. Yeah, well, right. This is not surprising. Yeah, this is not surprising. What is a little different here from the previous case is that I somehow need, I mean, I stated these four things. I never really explained how they're related to each other. But in the proof of A, in the proof of the reduction to a maximal torus, I need something about the connectedness of the automorphism group. So you can see this, I mean, of course, such things are proved by induction on the number of lines in the chain, but you can already see this when you try and start. So if X is the union just of two lines, I'll let Z be the node in between them. And suppose I have a principal G bundle on this union of two things. Well, on each component, it does reduce to a maximal torus. So I have sections SI of ET restricted to XI. Let's write it this way. Okay. Of course, if I choose them, randomly, they won't agree on the node. So can I make them agree on the node? Can I force S1 at Z to equal S2 at Z? By force, what I mean, of course, is that I have that group acting, the automorphisms of V and the Weil group. And that's exactly enough. That's exactly what I need to be assured that I can bring these two sections into agreement. Because right, I can act by automorphisms, by gauge transformations, basically on the two sides, and by the Weil group. So, I mean, again, think about where these are vector bundles. I can act by automorphisms or permute the summands. Using D, I can show that the image of the automorphism group in G, if I trivialize the bundle at this node, then I can look at the automorphisms of E at the node, give me a subgroup of G, and I get the parabolic precisely that appears in the Harder-Narasimhan reduction, C. So now I have any two points in G that are S1 of Z and S2 of Z. By acting by these three groups, I can bring them together because G is, after all, thanks to the Bruja decomposition, any element of G could be expressed as something in P1 times something in the Weil group times something in P2. So, so the Bruja decomposition is sort of what does it for me. So more generally, if I try and work by induction, so if xn is a chain of n minus 1 lines, and x2 is p1, and I proceed by induction, well, then I don't have any more, right, because of this example, I don't anymore have a Harder-Narasimhan reduction on x1. Nevertheless, it's still true, so I can prove that this image is still a parabolic. By a sort of tie-breaking argument. I mean, I do know by induction, I know that a bundle on x1 is now this chain of n minus 1 lines. I know by induction that my bundle here reduces to a maximal torus. I ask, well, what are the possible values that global automorphisms can take here? And then it has to do with the it turns out to be the parabolic defined by some tie-breaking condition. I have a co-character lambda here. It either has to be positive on the root space, or if it's equal to 0, this one has to be positive. Or if that's 0, then this one has to be positive, and so on. That's what the parabolic in question turns out to be. So even though I don't have a Harder-Narasimhan reduction, I still get what I want from the Bruja decomposition. And then maybe I'll say about B that the Picard group of a chain is a free abelian group on n things, and so the Cartier dual is connected. And so that's okay. People always ask, well, is this really a property of chains? Isn't it possible something like this is true for trees? And again, there's some elementary counterexample. This is definitely false, and for much the same reason as all the other things. If I just take this extremely simple tree, I could take the trivial bundle here, and I could glue it to 3 copies of O plus O1. Where again, I glue the O1 factor to different subspaces in this two-dimensional vector space here, and then, game over. It's just the same example comes back over and over, absolutely. All right, so the last thing that I'll say is just that what we actually need in our other paper is some equivariant version of this, and so we have to stick our toes into the world of Artin stacks as opposed to these Deligne-Mumford stacks. So let's say I let xn be this chain of n lines, as before. But now I have the n copies of the multiplicative group acting on the n components of my chain. And if I take any subtorus, I can ask about principal G bundles that are equivariant for that subtorus. And if you think about it, you might say, oh, the equivariant case will trivially imply the non-equivariant case, or maybe vice versa. Well, neither of those things is true. I mean, if you know it equivariantly, you don't know it non-equivariantly, nor do you know the reverse. But nevertheless, it works. It's the theorem, what am I up to? I guess 4. Says that A, B, and D hold in this case. If you have an equivariant principal bundle on this chain, then of course the torus will act on the fibers at each fixed point, in particular at each node. So S goes into G action at, say, at the last node. Well, there's a, right. If I trivialize the bundle at the last node, then there's, that gives me a homomorphism from S into G. And I again need to use the Bruhat decomposition, but not for G itself, for the centralizer of the image. And whether or not that is connected, I still have a statement of this form that G is equal to P1W, P2. The Weil group will take me even to the other components. And so, again, everything works out. Sorry, I've already run over time, and there are even more examples, as I said in my abstract, chains of footballs, chains of gerbs, and so we can hybridize the things that we have. But no individual example is that important or interesting. It's more just to open up the possibility that this Grothendieck splitting phenomenon is not unique to P1, and that therefore one can study moduli spaces of such objects, as I tried to indicate 2 weeks ago. Okay, thank you very much.
Any questions?
No way, look at me. Yes. But how's mostly our chains and footballs related? Likely these categories shouldn't be that.
Well, I mean,
Derived categories, or maybe with that story?
I don't know. I mean, is there some geometric, is there some correspondence, or some geometric relationship between a chain and a football? I mean, the way that they've been related for us is that, at least at some point in what we thought about, we had to consider chains of footballs. You have the footballs and you can glue them end to end. But are you saying that there's some transformation that would, some push forward or something that would relate?
I don't know. I mean, the cotangent bundles are sort of the same. I mean, the pi correspondence tells you that. But whether they're actually the same, we don't have to think of
The cotangent bundles are sort of the same? What do you mean?
I mean, the derived equivalent.
Oh, I see.
That's one way of interpreting.
A chain of, a chain of what length in a football with what stabilizers?
Right, if you concentrate on one P1 in the chain,
Yeah.
you count how many guys there are coming out either end. That will give you the M and N football.
Ah, I see.
Or plus one.
I
We could try and work that.
haven't thought about that at all.
Maybe that is you're contracting those two ends and you get something that's looks like an AN.
Yeah, I mean, the chain is the exceptional curve. If you partially resolve, you get a football.
I see.
Any more questions? Okay, so can we thank